Okay, so I think, oh, you did have a homework assignment to do today, but I think are there any I don't think there's any, I hope there's not any questions. Yeah. I mean, I just plan to not spend very much time on that. Hope that's all right. Are we good?
Yeah.
Because we have a couple things we need to do today. Okay, first thing we're going to do is, have you ever wondered about how the switch statement works?
Yes.
And also, thank you. and also, it's my plant. And also, have you ever wondered why in the branch instructions there's only two addressing modes, namely, what two addressing modes?
Immediate and index.
Immediate and index. And have you ever wondered what's the deal with indexed addressing with a branch instruction?
Yes.
Because now that you've actually translated and you know that those are the addressing modes that are legal, you know.
Well, I guess, I don't know why there aren't more legal addresses.
Well, it's only those two that are useful.
Okay. We would want to like branch to what is stored at a place in memory with direct or something like that.
Yeah. Okay, but now check this out. Those two issues are related. And I think this is something that's really, really slick. Now, the first thing that I want to state is that a switch statement is not just a nested if statement. Are you with me?
Okay.
In other words, a nested if statement, it would be if this case, else if the next case, else if the next case, else if the next case.
It's a branch.
It doesn't, well, I know, but an else if goes through and each one, it tests the first one, then it tests the second one, then it tests the third one, then it tests the fourth one. A switch statement does not do that. A switch statement does case this, and boom, it goes directly to the one without doing the test of the individual ones in between. Are you with me? Yeah, so I like the way you're thinking. It's like a table lookup. In fact, it is a table lookup. In fact, the name of the table is called a jump table.
There you go.
It's called a jump table. So what happens is, what the compiler does, oh, and by the way, guess who invented this? You know Tony Hoare of the Hoare triple?
Oh, yeah.
He actually invented this, yeah.
So Dexter's answer number 1, Tony Hoare's answer number 2. I think there's a third one too.
And so here's the idea. The idea is that each one of those cases in a switch, what you do is that case is the index. That case is the index in a jump table.
Okay.
And the jump table contains the address of where to go for that case. Are you with me? That's sort of like the high order idea. Now, in order to implement this, we're going to learn a new dot command. I think this is well, we never do use the dot burn command, but this is the last dot command that we're going to learn. It's the dot addrss command, and here it is on this slide, that dot address command. Address without the E. Now, here's the thing. Every dot address command must be followed by a symbol. So this time you don't put a number or a hex or anything there. So over here, if we say dot addrss, and here we have a symbol alpha, right here, then code does get generated. And the code that gets generated in the object code, it's the value of the symbol. But what is the value of the symbol?
The address that places.
The address of where that alpha is stored.
What about dot equates?
Oh, okay. In the first, you never use that combination. If this symbol were defined with a dot equate, then that value would be. Well, I mean, there's nothing illegal about it, but it would put that value there.
Okay.
So we normally don't use this. If alpha has been defined with a dot equate, we normally don't use it. But see, well, here's the thing. So down here in the code somewhere there's going to be an alpha. Say there's an alpha colon and then there's blah, 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 blah. Are you with me? Then up here, if you say dot address alpha, what goes to here is the value of this alpha, which is the address in memory of where this code is.
Okay.
Now, so does everybody understand how the .addrss, the .address command works? Are you with me? Okay. So we use that to implement the switch statement in conjunction with, get this, indexed addressing for the branch. Yeah?
Yes.
Okay, so here's what you do. Here's what we do. Here's what the compiler does. It sets up a jump table with the .address command. All right. So now instead of having an array of numbers, or an array of ints, or an array of chars, what do we have an array of?
Addresses?
We have an array of addresses. And how do you access an array? You put something in the what register? You put something in the index register, right? And then what's in the indexed register is the offset
From the...
from the address of the first byte of the table, the array. Are you with me? And boom, and that's how you access that one directly. So no else if, else if, else if, else if in between. And that's just called a jump table. Right? So you set up a jump table with the .address command. We use load index to load the index register with the switch value. And now, how many bytes does an address take? 2 bytes. So we have to do our ASLX, because an address contains 2 bytes. And then we execute branch with indexed addressing. Is that slick? Now here's how we're going to illustrate it. We're going to illustrate it with this C++ program, and let's see if we can, I think we can write this one pretty quickly. Okay, so check this out, you guys. What do we have? We've got int main, int guess, cout, pick a number, cin, guess. And what is guess is an integer, right? And so we can either guess 0, 1, 2, or 3. Right? And then we do switch, guess, and now what do we have? Case 0, cout, not close, break, case 2, cout, close, break, case 3, cout, right on, break, and case 3, cout, too high, and then cout inline, okay? So here we go. What's the first one?
Branch to main.
Okay. Branch to main. Yeah? And do we have any local variables?
Yes. Guess.
Oh, we do. So what is guess? It's an int, right? So what will that be? So guess, here's guess. And because it's local,
Dot equate.
we dot equate. And where will it be on the stack?
Here.
Yeah. Dot equate 0. And then here's main. And what's the first thing we have to do in main?
String output.
No?
Oh, we just sub
Bzz.
SP. Sub SP.
Yeah, sub SP. And how much?
2.
2 immediate. And we allocate
Guess.
pound. Oh, here, guess we need what? This is a local. Pound to D is right, and this is pound guess, right?
Now we can string output.
Now we can string output, so we'll do stro, and then, you know, message 1. Let's just call this message. Direct. And then, okay, and now cin guess, so what is that? What kind, it's Deci, right? Deci,
Guess.
guess, stack relative because it's local. All right? Now, watch this. Here comes the interesting part. We say switch guess. Okay? Now, so typically what happens is, the way we're going to do this with our compiler, imaginary compiler, is we're going to put the jump we're going to put the jump table right here in this code, and because we're going to be able to branch around the jump table. Okay, so we're not going to put it at the bottom, we're not going to put it at the top, we're going to put it right in with the code. It's very convenient to do it that way. So now, so what do we have? So how do we do the switch guess?
So you do the dot address.
No, we don't do the dot address now, because see that if we put a dot address in here now, there would not be instructions. You know, we would not be executing instructions. We would be.
Is the dot address used as an operand?
The dot address is used to construct the jump table, which will come later.
Okay.
Which will come right at, well, which will come after the branch.
Okay.
So we need to do the instructions that actually
We need to like
that actually do the branch.
so load the index register.
So we load the index register. That's right. So we load the index register with
Guess.
guess using what addressing mode?
Stack relative? No, direct.
Guess.
Well,
What kind of a variable is guess?
Local.
It's local. So what is it?
So it is stack relative.
Stack relative.
because we want the value of it, right?
All right. And now, so that's in the index register. But every
So now address
address is 2 bytes. So what do we do here?
ASLX.
ASLX. Okay, and now what do we do, you guys? Now this is really interesting. So now, see, where do we branch to?
To the switch.
Well, here's what we're going to do. It's going to come later. We're going to so we're going to branch. What we're going to do is we're going to branch to guess JT. We're going to branch to our guess jump table. And what addressing mode are we going to use?
Direct.
Index.
Indexed. Are you with me? Now it's kind of, well, okay, yeah, you would, it'd be hard to be with me right at this point because we haven't actually shown what the jump table is.
Right.
So now what we're going to do, this is an unconditional branch. Are you with me? Mm-hmm. So the next statement here doesn't have to be, we can put we're going to put our jump table right here.
Because we don't care.
Because we don't care, because we're going to branch to some other god-awful place anyway, right? So, so out there in the Tules. So here's going to be our, so this is going to be our guess jump table. And it's going to start right here. And now, what do we want to put in this table?
0, 1, 2, and 3.
Well, we want to put the address of the start code. Yeah, this is going to be kind of tricky to understand as we go because we're actually going to be using symbols that we're not defining until later.
Right.
But see, what's going to happen is we're going to have a label. We're going to have a symbol for case 0 and a symbol for case 1 and a symbol for case 2 and so on.
Okay.
All right. So here, so this guess jump table, what we'll do is this will be dot address ADDRSS, and we'll just there's a symbol coming up later, and that'll be case 0.
So why are you branching to the next line? Is that...
No. Well, we're not branching to the next slide because this is indexed addressing.
Right.
You'll see. You'll see very shortly. So this is the first part. This is the first entry in the table. The next entry in the table is what?
Address case 2, case 1.
Yeah, case 1. And then the next entry is going to be address case 2, and then the next one's going to be address case 3. Are you with me? So this is the table. So this is the jump table, and And guess JT is the operand here, but it's indexed addressing. And so now what we'll do is at this point we're going to put the code for case 0. So we'll put a symbol here, our case 0 symbol here. And this is what we're going to do with case 0. Now what code do we have to do for case 0?
Output.
It's a stro, yeah?
Show message 2.
Yeah.
Or message 4.
See, yeah, actually I called this one
Message 0.
message, so I could call this one message 0. So this is going to be a stro
You did it.
message 0. Are you with me? And addressing mode is what when you do a stro? Direct. And now what comes after that? What's the next thing after that?
Break.
Break. So now what do you suppose break is?
Branch to edge.
Branch to end the switch, right? Okay, so this would be BR and switch. And now continuing on, now what case do we have?
Case 1.
Case 1. So here we'll do case 1. And this would be a stro message 1 direct. Is that how we do the stros?
Yep.
Direct. And then branch to end switch. And then case, etc.
Yep.
Now let's see if we can understand exactly how this jump works. Now look, this is branch to guess jump table using indexed addressing. Let's suppose that the person, oh, did you just figure it out?
Yeah, that's cool.
Is it way cool? Yeah, it's very nice because we already know how indexed addressing works. So what happens, the way this works, let's suppose that the user, when we do deci guess, let's suppose that the value that got input into guess is 1. All right? Then we load X with the 1, we ASL X, and so that makes it 2. The index register 2. Now we branch to guess jump table, but using indexed addressing. So where do we branch to? Well, we take guess JT, that's the operand specifier.
Right.
We take that plus whatever's in the index register. What's in the index? So what is this value? What is this guess value?
Okay.
That is the address that guess JT. The value of this is the address of where this is.
Right. If you
Right?
add 2 to
And then you add 2 to that, that's the address of where this is. But what is in that memory location?
the address of case 1.
Yeah, the address of case, so boom, it jumps directly to case 1. Is that slick or is that slick?
So guess JT is the address of that .address line.
Guess JT is the first byte, is the address, see here's the symbol. It's the address of the first byte
Right,
of the jump table.
right. And then case 0 is
the address of the code that actually executes for case 0. Now I think what we should do is, let's take a look at the code now, and I think you'll see the actual specific values. Okay, so check this out. Hope we did it right. Sub SP2 immediate, is that right? Guess equate 0. Sub SP2 allocate pound guess. Stro message, oh, I called it message in instead of message, but you got that. Pick a number, 0 to 3. Deci guess stack relative. Now, check this out. Load index register, guess, stack relative addressing, ASLX, and now, check this out, you guys. You see, where is guess JT? What line is it on?
13.
That's on at 1.3, hex 1.3, right? But now what value is stored there? 00 what? 1B. Well, now what is 001B? Well, it's the address, it's .address case 0. Well, go down to case 0. What line is case 0 on? It's on line what? 001B. Are you with me? And then what about see that code that's generated? You see, look, starting at 0013, what's there? 001B, 0021, 0027, 002D. What are those addresses? Those are the addresses of what? Of where the code for those cases are. Is that slick? So you see, boom, it goes straight there. No nested if. And this concept, by the way, do you remember polymorphic dispatch?
This is polymorphic dispatch?
Well, this is actually a technique for polymorphic dispatch.
Using these tables.
Using, jump tables.
Oh.
But you get the idea of what a jump table is. It's an array of addresses, basically, and then you go, and then depending on which one you want to go to, boom, you go to that one.
And this is why we have indexed addressing modes on branch?
Yes, yes, and this is the use of it, using indexed
Jump table specifically.
jump tables specifically, yeah. And you can put the jump table right here in the code because this is an unconditional branch. You see, then it's not going to it's not going to execute this. It's not going to execute this as an instruction. It's going to use this as the address of where it's going to go to if x is 0. If there's a 0 in the index register.
You could put the dot address anywhere you wanted.
Actually, you could. The only thing is they got to be contiguous.
Yeah, right.
You know, you can't put gaps. You could put them all up at the beginning, or you could put all at the end. Yeah.
Okay.
But I figure, you know, the branch is right there, the jump table is right there, you can see it right there, so our style will be to put it right like this. Because this is an unconditional branch.
Right.
Kind of unconditional. You see, but it depends on what's in the index register. So
It branches to a different
it branches to a different place,
It will
depending,
branch.
but it will branch. Yeah. So yeah. So it won't try to interpret this as an instruction. That code there is an instruction. And then here's the messages. All right? Well, it sounds like you're with me. Okay. Well, so that's the first thing we wanted to do. Now, the second thing we want to do is we want to see how pointers are implemented. Now, what is the memory model of C++? Right. Dynamically allocated variables are stored on the heap. So now we're going to get to see a heap.
Oh boy.
Cool.
Nice.
Heap's been this like magical, mystical thing.
Yeah, they are. It is a magical, mystical thing. Yeah. It's a lower level. What is abstraction? Hiding detail. That heap has been hidden. The details have been hidden. So now we're going to see what the heap is. All right. So we're going to learn a new addressing mode. And this is our last one. So after we learn this one, we'll have all eight. We'll have all 8 under our belt, our collective belt. Okay. So the topic here then is global pointers. Now, everybody knows, what is a pointer? What have we always said a pointer is?
The address.
It's an address.
Of an object.
Yeah, it's an address of some data, of an object. Okay? And in PEP 8, all addresses are how many bytes? 2 bytes. So if we have a global pointer, you allocate storage for a global pointer the same way you allocate storage for any integer with dot block. So we allocate storage for the pointer with dot block 2 because an address occupies 2 bytes.
What's the hashtag? Like, what's the
The hashtag.
trace tag?
Trace tag? Oh, good point. Because it's an address, what will the trace tag be?
Pound 2H.
Pound 2H. Because it's a 2-byte hexadecimal. You want to display those in hex. Because then you can relate them to the addresses at the other parts of memory. I think you'll also see that this is a really cool demo. Okay, the second thing is you access the pointer with direct addressing because it's global. Now you could, if it's local, then you could access it with stack relative. Same kind of thing, right? And then you access the cell to which the pointer points with indirect addressing.
What? We haven't done that one yet.
I know, but now we need to do indirect addressing. Now, do you remember what is indirect addressing? Here, there's a hierarchy here. Okay, so remember, immediate. So what was immediate?
That's the first one.
Yeah, but what is it? It's the operand. It's the operand equals the what? No, immediate. The operand is the what? Is the operand specifier. And then we said, that was immediate. And then direct. Now how did direct work? It's the operand is what? The mem of operand specifier. So what's the meaning of this? The meaning of this is that the operand specifier is the address in memory of where you go to get the operand. Well, indirect is what? It's actually, immediate is actually direct deferred. Are you with me? Remember how we did deferred? Deferred means it's the mem of that.
So it's mem obspec?
Yeah, so indirect is actually direct deferred. That's all it is. It's another level of indirection. Mem. So now what does this say? This says, and think about it, this is what you have to do to access the value that the pointer points to. This says that you take the operand specifier, you go to that location in memory, and that location in memory is the what? Is the address of where the operand is. Are you with me? Is that good? Okay. So here we go. Oh, haha. Now there's one more thing that we need to do. Oh yeah, now this you definitely need to know for the final. There will definitely be this one. Okay, we are going to have. What's the one thing that you have to do with dynamically allocated variables? You have to allocate them with what?
New.
With new.
Oh, and some space.
Yes, you have to allocate them with new. Now, do you remember what new does in C++?
Allocate space.
It allocates space for the variable and then does what?
Calls a constructor.
Well, it does that, but we're not going to do object. Yeah, actually, that's a good
That's
point.
object, okay.
Yeah. There's a more complicated memory model for object-oriented programming.
Surely.
Okay, and so that's beyond the scope of the book, of this course. But anyway, what does new do when you have just a simple?
It returns a pointer.
Yes, it allocates the storage and it returns a pointer to it. Okay, now that sounds suspiciously like a function, like something that a function would do.
Allocate space and then returns.
Yeah, yeah, and return, yeah. So, it could be like a non-void function. But, now here's the thing, you guys. It's not going to be implemented like a function is. If it were a function, then we would have to give it what? What would we have to give it? If if new were a function, what would we would give it what?
Parameters.
And what parameter would we have to give it?
The address?
No, it would return the address. Are you with us? So it would return it would be a non-void, and it'd have a ret val, and it would return the address. But what parameter would we have to give it?
What we're allocating, right?
Yes, and what would it have to figure out? What would it have to do with that? If we gave it, what do you mean, what we're
The
allocating?
name of the variable?
Well, if we gave it the name of the variable,
We'd have to give it like what it is. Is it like 2 bytes? So it's
yes, what it needs to know is how many bytes to allocate
Yeah.
somehow. Now, the compiler can figure out how many bytes to allocate, right? Or we could just have, it could just be a function and we could figure out how many, well, the compiler would have to figure out how many bytes, and it would give it the number of bytes to allocate, and it would return a pointer to that allocated. Are you with me? Now, if we did it that way, if we did it like a function, what would every time you call a function,
The new
and a
frame.
new stack frame, and not only that, it's non-void, so what would we have to do? Storage for the return value, and then the parameter, we'd have to do the parameter, and boom, and it would do, and then done, okay? Now, but with new, first of all, new is not recursive. New doesn't call any other functions. We don't need a return address. So here's the protocol for new. What you do, the way this new operator is going to work is your main program is all you have to do is put the number of bytes that you want to be allocated in the accumulator.
What?
So we're not going to push it onto the runtime stack. We're going to put it just in the accumulator. Are you with me? And then you call new. Are you with me? So new is just going to be a little subroutine at the end of our program. We're going to call new. And then what's going to happen is you can assume that after new has been called, the index register is going to contain the pointer to the allocated bytes. So what, well, that's the way new is written.
Okay.
That's the protocol. So notice that this is different from the protocol for calling a function. Instead of using the runtime stack to pass information back and forth between the calling and the called, what are we using? We're using registers in the CPU. Now, do you see that this makes it super fast? Because we're bypassing, sub SP and allocating, and we're bypassing, and furthermore, nothing is in memory. We're not doing anything to memory, right? So this is super simple, super fast. And not only that, but this is an important example of, there are protocols like this at this level of abstraction in systems programming. You see what I mean? Operating systems can if you can pass information back and forth between routines this fast, then in an operating system, that's the way you want to do it. You see, so we just bypass the stack altogether, and it can be super fast. But this takes a little bit getting used to, because every time we've called a function before, what have we had to do? We've had to go sub SP, retval, blah, blah, blah. Now, all that's out the window. All you do is you put the number of bytes you want to have allocated in the accumulator, call new, and then you can, instead of doing, add SP or whatever at the end, you just, boom, the index register contains the pointer to the newly allocated storage. Are you with me? Okay. Now, does this example look familiar? Mm-hmm. I think we looked at this example earlier in the course, did we not? Plus, I think this is probably the same example that we used when we reviewed C++ and data structures. Mm-hmm. I have a tendency to use the same example over and over again.
Why not?
Why not? It works. So check it out, sports fans, figure 6.41. So let's draw our memory map, or our memory model. So what do we have? A, B, and C, but what is each one of them? A global pointer. So how do you allocate globals? So A, okay, so first branch domain.
Do we actually put a star next to it, or do we just say?
No, do not put a star. Okay, so A is dot block 2, and this is a global pound to H because it's a pointer, so its value is an address. And then B dot block to pound to H, C dot block to pound to H, and here's main. Okay? Now, what does main say? First of all, do we have to do any sub SBs here?
No.
No, because they're global, right? Okay, so now you guys, how do we do A gets new int? Now remember what the protocol was. We're calling new, right?
Load the accumulator.
So we load accumulator to addressing immediate. Now why do we do this to immediate?
Because we have the number of bytes.
Yeah, this is allocate 2 bait. Allocate O. Yeah.
It's 2 bytes because an int is 2 bytes? Is that what we're...
Because an address is 2 bytes.
Oh.
Now here's what our debugger does. So now what do? We do call new. Are you with me? Now,
You store it.
yeah. Now here's what our debugger does. What our debugger does is, when you say call new, it allocates something on the runtime. Or sorry, not on the runtime stack. It allocates something from the heap. Our debugger is actually going to trace the heap as well. Are you with me? So now what we need to tell it, we need to have a way for it to label the heap. So what we do here is we put pound A. And so new, you can't use, yeah, here's the one thing. Don't ever use new as a symbol. Okay? Because it'll confuse the debugger. Are you with me? Built into the debugger is the symbol new.
So never. Okay.
So never use new as for some other symbol. You know, you can say my new or his new, but you can't
What
say.
does it do?
Well, I don't know what it would do. It would get very confused. Well, the debugger part would get very
think it would
confused.
just
It
pick
wouldn't.
one?
Save.
Do you think it would just pick either our symbol or the one that's preset?
No, oh, no. If you did it, the only way this will work is if new is the start
Words that are...
address of the new routine, which is at the bottom of the program. So it would be multiply defined symbols. But what I'm saying is, if you didn't have that new and you had another program that didn't use the heap and you just called it new, it would be confused here because of this trace tag. Okay, and now what can we assume? Now check this out, you guys. What can we assume? At this point, we load a and we call. At this point, what can we assume?
That the index register has a pointer.
That the index register has the pointer to the memory that's been allocated. So what do you suppose we should do now?
Store the index register.
Store the index register. Is everybody clear on that? This is because of the calling protocol for new. But now, where do we want to store? Well, what does our program say?
Store to A.
Store it to A. Addressing mode?
Direct.
Direct, because A is a what? Global variable.
Right.
Now, is everybody with me on that? All right, so now we can move along. So what's the next one? B gets, okay, so load accumulator to immediate. We shouldn't need to do this, but,
Wait, what about the start A gets 5?
oh, is there a statement in between there?
Yeah.
Oh, sorry, I jumped ahead. So now, yes, now how do we dereference? How do we do star A gets 5?
That's what A is pointing to is 5.
Yeah, what A is pointing to is 5. So how do we do anything gets 5? What do we do? Load accumulator what?
5 immediate.
5 immediate, but now what, sports fans?
Store accumulator.
Store accumulator
Direct.
A indirect.
That's it.
Is that what you said?
I said non-direct.
Indirect.
I was
Yeah.
like, what? It's
So it's the N.
N. Are you with me? Because what does A contain? The address of where the 5 is stored.
Right.
Okay? Is everybody clear? Because A contains the address, so it's one level of indirection.
Makes sense.
Yeah.
It sends it to the address of day, which is there, which folder.
Yeah, and that 5 will be in the heap.
Okay.
That 5 will actually be, yeah, we don't know what, yeah. Okay, now let's do the B.
Now we can load
Load accumulator
to
2 immediate,
allocate.
which is call new. And here we have to put the trace tag, what, pound B?
So you'll always load accumulator with 2? Or
Well, in this case, well, there's going to be another example where if you're dealing with a struct, and you allocate a whole struct, then it's how many bytes in the whole struct?
Okay.
Meaning like an array?
No, a struct.
How does struct teach?
You know, like, struct is like a class, the attributes of a class. A struct is like a class.
Is that next?
Yes. Okay, but in this case, or if it were a character, it'd be 1. That's another example. That's another example. Are you with me? Okay, and now what? Store X, B, direct. Okay, and then does B get something here?
Yeah.
So now how do we start B gets 3? Load accumulator what?
3 immediate.
3 immediate.
Store accumulator B indirect.
Store accumulator 3 indirect. Now you guys comes some
B.
B. Now you guys comes some pointer manipulation. How do you do C gets A? Ha-ha! Now think about this over here. So now you guys, how do you do C gets A?
C needs to get the address that A has, right? Or the address.
Well, whoa. When you're doing C gets A, yeah, now this is really good. What are you doing when you do C gets A and C and A are both pointers?
C gets what A points to.
Yeah, C's gonna get the address that A has.
So do you know the
Yeah.
address?
So what addressing mode do we use?
Direct.
Load accumulator.
So load accumulator what? A, addressing mode though.
Direct.
Excellente. Not indirect, but direct.
Yeah.
So you store
Store
it.
accumulator.
Because, and then store accumulator what?
C direct.
C direct. Because those are addresses, right?
Why would it be indirect?
It's not
Yeah,
indirect.
it's not. Why would
Okay, yeah. Well, I mean, you think, oh, pointer, indirect addressing pointer, yeah. Okay. So that's, and then what's the next one? C gets A,
Load accumulator B direct.
A gets B, so load accumulator. So this one is C gets A, and now we're doing what?
A gets
A gets B, so load accumulator
B.
B direct,
Store accumulator A direct.
store accumulator A direct. And now don't we have some dereferencing here? Now what do we have? We have star A gets 2 plus star C.
Load
So
accumulator 2 immediate.
load accumulator 2 immediate.
And then
And now add accumulator what?
C and
Add accumulator C indirect. Because that's what the, now you like pointers better? Yeah.
and then store accumulator A direct.
And then store accumulator, A, but what?
Indirect.
Indirect.
They make a lot more sense now.
They make a lot more sense now. Good. Yeah, well, that's the whole idea. I'm glad that that's what's happening, because that was the whole idea of this whole design of PEP 8.
Of the whole
Seriously, I mean, that's the whole purpose of this is to shed light on exactly how this stuff works at lower levels of abstraction. Okay, and now what? Oh, but now what do? We have a stro. Okay, so here we have a stro and then message 1 direct. And now what are we outputting? The value of A star. So what do we do?
Deco.
Deso A indirect. etc., etc., etc.
Actually,
Is that cool? Do you want? Shall we do a demo? Oh, here. Let's take a look at the code. Is our code correct?
Should be.
Well, check us out. I mean, we were thinking this through. Is this right? Are we? Does this check out all right?
When do you ever deallocate? Like, you know, you just put hashtag A, hashtag, or
Oh, that's a really good. Yeah, that's really good.
is that when you do delete?
Yeah, that's a really good question. Now, you wanted to know how the heap was magic. Okay, now, here's the thing. This heap, I'll show, actually, we won't do a demo. We'll start at the class next time. We'll do a demo at the start of class next time, and I'll show you how new works. But doing delete is beyond the scope of this course.
right.
So is all this heap does is this heap only has a new, and it doesn't have a delete.
So it's only
Because
for
delete,
pointers.
huh?
So it's only for pointers.
Well, but with pointers in C++, in order to do in order to not have a memory leak, you have to have a delete. You have to, the programmer has to do his own delete,
Right.
right? And whether the programmer does the delete or whether the garbage collector, automatic garbage collection like in Java does the delete, still you have to be able to delete. Now what happens is, so when you store, now think about what happens. Like let's move over here. So what happens is, if this is the heap, and this is memory. So suppose that you allocate this much for one variable, and then you allocate this much for another variable, and then you allocate this much for another variable, and you allocate this much for another variable. And then if you delete this one, then what you have to do is, this one now becomes free. Are you with me? And then if you want to allocate for another variable, instead of just allocating from here, if it will fit here, what should you do? You should allocate here. But what if it doesn't quite fit there? Then you might just have it go here, and now this part is the part that's free. And the way that you do that allocation, and the way that you do that delete, the way that you actually do this, there are algorithms that do that.
So it's like a memory saver.
It's a memory, well, what it is it's the heap manager. And we actually used to, in the data structures course, we used to actually teach how to do that. We actually would do the algorithms for how to do that. Because it's a very common, all dynamically allocated memory has to do this. It has to do this. But like I say, the details of that are beyond the scope. But you can look at, beyond the scope of the course and of the book. But you can actually investigate that if you Google, like heap management algorithms. All you have to do is like Google, and you'll see there's several different systems. And the question is, do you want to put it in, if you have a fixed amount of heap, do you want to put it in the first one that fits, or do you want to do the best fit? And there's different strategies for doing it so that you can manage that all very efficiently. And it gets a little complicated, but it's it's no more. You could certainly handle that. Like I say, we used to do this in data structures. It's kind of now it's kind of a heap management has kind of like a solved problem. There are it's been very well studied, and so the different strategies for doing heaps, like if you get into the Linux internals, you'll see. Heap management is all part of all operatings. It's kind of like an operating systems topic. Okay, and it's beyond the scope of this book. So the new that I'll show you at the beginning of class next time is all it does is allocates. You can never deallocate. So delete, we're not going to do delete. Okay, anyway, so good deal. See you next time.